Polynomials have the power to solve many real-world problems. Throughout math, we often use it to solve complex problems without fully understanding it. First, we will start with a zero-dimensional quantity, also known as a scalar. Scalars represent only magnitude. Any number that can scale quantities is considered a scalar. For example, 2 can scale x to 2x, twice the quantity. 1 can scale x to x, which retains the quantity, and 0 can scale x to 0, which eliminates the term. One thing to note here is that scalars can have a sign, so they can change the direction of a dimensional quantity. First-degree polynomials are essentially straight lines that have a direction and a magnitude. By direction, I mean positive and negative. If a body goes forward, the change is positive. If it goes backward, the change is negative. Vectors are essential for dimensional understanding. A vector is a quantity that has a direction and a magnitude. Here's how to write them. If A is a vector, then depending on the dimension, A can be written as A equal, in the first bracket, x coordinate, comma y coordinate, comma z coordinate, and so on. Or A can be written as, in the third bracket, x coordinate, y coordinate, z coordinate, and so on. In one-dimensional space, a body can either move forward or backward. Here, A equal x, and the equation of a line is v equal a plus kd. It is called the parametric form, where v is the resulting vector, k is the scalar, and d is the direction vector. The beauty of this equation is that it can be used in any dimension. Say we are working in the third dimension and a equal 3, 4, 5. We want to go towards 3, 6, 2. The direction vector d is 3, 6, 2 minus a is equal to 0, 2 minus 3. After k equal 2 seconds, we would stand on v. So v is equal to a plus kd, a equal to 3, 4, 5 plus kd equal to 2 multiplied by 0, 2 minus 3. So v equal to 3, 8 minus 1. In symmetric form, the equation of a straight line is, this equation works for 3D, though we won't use it here. In 2D, the equation of a line is y equal mx plus c. Here m is the slope. Slopes are the rate of change of the graph. In other words, derivative. Before going to the derivative part, let's talk a bit about vectors. Vectors are basically pointers, or a point in space. Suppose you were on a number line at 0, you moved forward and then went down. The question is for you, how do you express the whole action? Let's define a few things. Say you moved forward by v and went down by minus u. V and u are both natural numbers. V shows the action in the x-axis and u shows the action in the y-axis. So you write v plus minus u. It is correct. In fact, you can go about this with complex numbers, as they suggest an orthogonal direction to the x-axis. They are the key to understanding vectors. Derivatives are essentially slopes. More accurately, they are the instantaneous slope of any point of a graph. Derivatives are not in the range of this video, so I will show a method that traditionally isn't used. Let's say f of x is equal to ax squared plus bx plus c. To find the derivative, let's imagine x equal to y, then the equation becomes ax squared plus bx plus c equal to ay squared plus by plus c. Second-degree polynomials are polynomials that can have two roots, so it can have two intersecting points with the x-axis. A graph of f of x is equal to ax squared plus bx plus c has a vertex at -5 and two roots at -8 and -2. Let's see if we can bring them. We know the derivative is 2ax plus b, and setting it to 0 gives a position that has a slope of 0. So 2ax plus b is equal to 0 and x is equal to minus b over 2a. So the vertex should be minus b over 2a, and the equation to find the vertex is we know roots are only real numbers if the vertex is negative or at 0. Ax square, a scaled version of a square. Next, if b is a length, then bx is a rectangle and c is a constant. Divide the equation by a. It does not change the roots, but we get the real size of the square in front. Now, bx and c are scaled to bx over a and c over a. Half the size of bx over a, then reposition it. It indicates a missing square of a length b over 2a. Add b over 2a and subtract b over 2a, and you get the first derivative of the quadratic equation is 2ax plus b, which is a line with a slope of 2a. So 2a is the third derivative. The first derivative shows the vertex. The second derivative shows the concavity of the quadratic equation. Positive means concave up and negative means concave down. Say f of x is equal to ax to the power 3 plus bx squared plus cx plus d. Now a is just a scalar. We can divide it. So we get gx is equal to x to the power 3 plus bx squared plus over a plus cx over a plus d over a. Let's take the derivative of f of x and find the vertices. The derivative of f of x is 3ax squared plus 2bx plus c. Set it to 0 and we find the vertices. Now that we know the vertices, let's find them. Working out the math, we get third-degree polynomials enlight us with imaginary numbers by using complex plane. See, we take input as x-axis and output as y-axis. A cube equation works with 3 dimensions, so we need a third dimension to represent them. Notice, this time the first derivative didn't pass through the midpoint or the inflection point. C minus b over 3a, this term should be the midpoint of a quadratic equation. The second derivative of the cubic equation is a straight line, 6ax plus 2b. Setting it to 0, we get minus b over 3a, which is the midpoint of our quadratic equation. Now that we know the midpoint, let's visualize the cubic equation. Here, the first term is ax to the power 3, where a is a scalar and x to the power 3 is a cube. The second term is bx squared, where if b is a line, then it is a cuboid. The third term is if c is a square, then it is another cuboid. Finally, the term d is a constant, but we have two different cuboids. To understand it better, it is helpful to have more information, such as we haven't tried base shift yet. In the quadratic equation, the vertex gives a way to find the roots, so we didn't have to do it. Here, base shift are possible for three distinct places: the vertices to 0 or the midpoint to 0. If you work out the math for each, you will get OX, O1x, and O2x. See, for vertices, x term is gone, and for midpoint, x squared term is gone. Well, let's see the cubic equation. X plus b to the power 3 is equal to x to the power 3 plus 3bx squared plus 3b squared x plus b to the power 3. So, to be a perfect cube, b needs to be 3a and c needs to be 3a squared. Again, if we multiply x plus b, x plus q, x plus r, then you'll get. Looking at it, we can say b is the sum of every dimensional length, c is the sum of every dimensional area, and d is the cuboid made by b, q, and r. It is the very reason why cubic equations don't use the same function to solve for their roots. The depressed cubic equation is OX. Let's substitute x with a plus b. I didn't find any great explanation for why we do that, but it is helpful. OA plus b is equal to a to the power 3 plus b to the power 3 plus a plus b multiplied by 3ab plus b plus q. Set it to 0. A to the power 3 plus b to the power 3 plus q must be 0. So a plus b multiplied by 3ab plus b is equal to 0. So we get ab equal to minus b over 3, or b is equal to minus b over 3a. Substitute back into the first equation and you'll get a to the power 3 plus minus b over 3a to the power 3 plus q is equal to 0. Though it solves one of the roots and is pretty consistent with the result, it does not exactly suggest the same graph. Browse the link in the description and scroll down to the general group for the cubic equation. Turn on the graph and see for yourself. We have come pretty far into cubic equation, but one thing is yet to be covered, and that is the third derivative. The third derivative is 6a. Well, it is the slope of the second derivative, so what it suggests is the in-behavior of the function. Actually, I searched myself to figure out what its properties are, but it seems those explanations focus less on the graph than the second derivative. One explanation says it is the rate of change of concavity. It's kinda confusing.